Hello explorers and welcome to another video. Today I'm gonna talk a little bit about running workloads on GPUs. So today when you're trying to do things that requires a lot of computation, people usually either have a lot of CPUs or they use TPUs, or they can run a lot of the workloads on GPUs. And GPUs are really good when you are trying to do things in either a 2D context or a 3D context, because when you're trying to do those kind of workloads, GPUs are very efficient because they have already been optimized to do 2D and 3D graphics. So therefore they are really good to do matrix manipulations. So in order to start this off, I'm going to use a library called JCuda, and JCuda could be fetched by this dependency here. And JCuda uses a library from NVIDIA that is called CUDA, and CUDA is a workload library that you can download from NVIDIA, install on your machine. In Windows, you just install the binary package, so you download it and just install it and you're done. In Linux, you need to have it installed, you need to have the correct NVIDIA drivers, and you also need to have a kernel module called NVIDIA UVM. So that's a driver module that you need to have installed on your system. In Windows, you usually get these drivers with your standard NVIDIA drivers. So if you have an NVIDIA graphics card and you can run this, then you could use CUDA. And on the CUDA website, you also have a grading for your graphics card in order to know what kind of workload you can put on it. You could always build things that could be done on all graphics cards, but the more specific you can be and the more you can tailor your implementation to your graphics card, the more performance you will get out of it. So when we have put in this little dependency here, we start by running this very simple hello example where we create a pointer. We actually take this pointer and put that in the CUDA, so it will actually just create a pointer on the graphics card and then free that memory again. So this is a very simple example just to see that everything is up and running. And if we run this, it should tell us that we have a pointer somewhere in native memory. And the interesting thing by this little hello example is, even though you haven't installed your graphics driver correct, this could actually work. You could get a native pointer to your normal system. So this never failed for me, and I thought that okay, everything is set up, and when I ran the correct test, I wasn't running it on my GPU, so that was a bit strange. So let's go into something more interesting. Let's do some actual work. And we have a little example here where we actually use a kernel, and this is what we have here, this PTX file. And first off, to run a CUDA example, you need to set that you actually want exceptions to be thrown from your driver. So everything that is bad in your driver will throw an exception, so that's good for error handling, and so you see what happens. I'm not sure if it has performance disadvantage if it goes faster if you turn it off. I have it on because it goes really fast either way. Then you will init with this flag 0. It's what state you want to set your graphics card into. Then you create a device, a CUDA device, and you get that specific device from your system. And you also create a context, and these are used later. Then you will load this module. This is the actual file, this PTX file we talked about earlier. And from that PTX file we will fetch a function, and in this case add. So if I look at my kernel here, this ptx file is a module, and in this module we have the function add. It's a very simple C-like function where I have two floats I put in and I get the summation out, and it also have this n value to actually block that we don't run this out of the actual space of our array. So these floats here, all of these are arrays with a specific length, and this n tells the length of those arrays, so we don't pass past the end of them, because these calculations where you have a block of workload and then you say that this index of this block I want to work on, and this is the dimension of the blocks, so this is the size of the blocks, and then the current thread I'm working on. And this calculation isn't always even, so in some cases you can actually put some work on one of your GPU's cores and it actually falls outside of your actual workload, and then it should just not do anything, so you don't get any errors because of that. And when we have this file and want to run it as a PCX file, we actually need to build it. So we can only run PTX files or Cubin files. And Cubin files are actually CUDA binary files, and PTX files are something that looks like assembler but will be loaded directly into your memory card. So to create a PTX file, we can run nvcc, and in order to run nvcc on Windows, you need to have it in your path. So the CUDA libraries need to be in your path, so you can run nvcc because that's a CUDA tool. And you also need to have the C linker in your path, and in order to do that on a Windows system, you have Visual Studio installed, and you will run var args all on that bat file in your Visual C directory, and that will actually give you all the paths so you can find that specific exe file. And MVCC can take a few different parameters to it. One of it which is PTX, so it will create a PTX file, and then you can actually just run it with the current file that you want to compile. And then you get a warning that the SM2021 archetypes are deprecated. And I know that my card is actually an SM61, and I know that I run on a 64-bit system, so I could specify this here, but when you create a PTX file, it's not actually interesting, because a PTX file is just some kind of assembler, and to optimize it isn't that super interesting. When you come to binary files, it's very interesting, but to do this, we put in M as a machine, so we say that this is a 64-bit machine, and then we can say that it has an arch of SM underscore 61, because that's my capabilities of my graphics cards. So they have a table with the graphic cards capabilities, and mine are 6.1. I think there's a 6.2 also if you get an even newer graphics card. And after we have done that, so now we have the file, we have loaded this function, we set up that we want to run through 100,000 elements, and we create some inputs, and then we actually just go through and create numbers from 1 to 100,000 as floats in a huge array, and then we will create a device pointer, and this device pointer input A, we will take that device pointer and actually allocate a buffer of that size in floats on that device input, and then we copy our data from this host input that we created up earlier and over to this device memory. So now we have actually copied the memory into the GPU so we can use it later. We do the same for the input B, and then we will also allocate a result buffer on the GPU for the device output. And then we just say that we to our kernel we had 4 inputs. We had the length, we had the A, B, and the sum. So these are the device input A, device input B, and the output, and the first one was the actual number of elements. So now we have created all the parameters to our functions. Now we actually want to launch this. And in order to do that, we will give the GPU a block size it will work on. And in this case, we say that every block, that every GPU processing unit will get a block of 256. And then we create a grid with blocks of that size in our work. So by creating a block and then a grid of those blocks, we could actually say to the different cells in our graphics card that they will work on different data units. And that's what we do down here. We launch a kernel, we say how the size of the grid size is, and you see here that we have actually grid dimensions in X, Y, and Z, so we could work in a 3D space. And then we have our block size also in X, Y, and Z. And then we tell it how much shared memory they should have in between, so they can actually talk with each other. I'm not using that at all with my examples. And then we put the kernel parameters in, and those are sent to our function. And after we have run this kernel, we would need to synchronize so that everything shuts down and then we know that all the work has been processed. And then we copy the result of the output pointer to an output buffer here. So we have the host output. And then we will go through and actually check the result if we actually got the result of the 2 inputs added together as our result. So it goes through here and checks that it doesn't have any failures on the graphics card, and then prints the test has passed or failed. And then we need to free our memory so that we don't have any unfreed memory on our graphics card. So let's run this example as well, and the test pass. And as you see, that went really fast. And so this is the first example, just adding a lot of numbers together on our CPU. But I wanted to do something a little bit more interesting. So I wanted to do some image manipulation. And in order to see some kind of comparison, it's not that this comparison will be total. It will not show off exactly how much better it is. You just will get a feel for it. So we don't take any of these numbers for granted. But I have a little filter example here that you actually make a blur of an image. So this is a dilute or blur filter. And I say that you have a specific filter size. And then this is my little apply filter function. It will go through this filter and apply it to an image. It's not that important how I do this, but it's pretty much what it does. This is the for loop that is a little bit weird. I apply the filter 1 million times because doing this either way will go ridiculously fast. So I had to actually slow it down in order to see some differences. And then I run my filter here across the whole image, and this is my main function. I take some test image in, I make a grayscale of the image, I print the before image, get the pixels of the grayscale image, and then I will run my filter, get the result, and then put it back to the actual pixel set and write the pixels out to a result. So let's look at my test image. This is a nice little image of some landscape, and if we run my Java filter, I will first off get a grayscale image. Let's see, with this, the before image, it's quite sharp. And then after my dilute filter, we can see that there are some changes. Some of the fence posts are a little bit more blurry. Not that huge of a difference. The interesting part is here we have a time of 95. So it takes actually some time to run this. We run it a few times, 100, 110, 97. And so on, so, and 250. So it actually takes some time to run this. If we go to running this on the GPU, then I have pretty much the same as we had before. I will get a different kernel, and down here I will create my grayscale image. Still not that important, the implementation details. I have everything on my GitHub repository if you want to look into it more later. It's a Java CUDA example. You can find it on my GitHub. I will also put the link into the video description. I get the pixels, I create a pointer on my graphics card with the size of the image, and I copy all the pixels over there, and then I will also copy over the filter to the second argument, and then create an output so I can get a result back. And here we have my kernel parameters: width, height, pixels, filters, and output. Then I will create a kernel block with block size 32 times 32. So this is actually a size, how large of a block I want to give to the graphics card, and this is dependent on how much memory you have on the graphics card actually. So before we had 126, and this 32 times 32 is even larger, but I'm doing it in a grid of a 2D dimension. And then I will create a grid size, and I will supply all those with my kernel parameters and synchronize. Then just copy back the result and write my grayscale image to the result PNG here, and then free up my memory. But we saw here that I will use the kernel called Cubin, and to actually compile that, we can use the exact same command we used earlier. The only difference is that instead of ptx, we say Cubin. And in this case, it's very important that you have an architecture and a machine, because this will actually be very much more compromised. So we cannot actually look into the assembly that we ran earlier. So this is some kind of assembly-like language that we can read for the earlier example, but this Cubin file is binary, so we can't read that. Maybe we can decipher it and read it, but it's not humanly readable from just looking at the file. So if we run this CUDA filter, and another thing to also know here, that I start my counting before I copy my values to the graphics card. So before I copy any memory, I start the clock, and then I read after I copied the data back from the GPU. So if we run this CUDA filter, it takes 13 milliseconds instead of 100. So that's a lot. Just for fun, we could move this so we only look at how much time the calculation on the graphics card takes. So no copying, just the actual execution. And that takes 1 millisecond. So the most of the time is actually spent copying data to the graphics card. The actual processing takes no time at all. I wonder if I can actually push this up to 64 because I have a little bit more memory on this machine. No, invalid value. So it actually gets too large if you push these sizes too large. Then you won't fit it into memory when you work with it. So let's look at the CUDA result, and it is a bit blurred. So it's the exact same image, nothing different here. So the Java and CUDA example was exactly the same. We can now also look into the CUDA test kernel. We have it here. We have the width, height, image, filter result. And here you see that I run my full filter over the image and then get the result back. So it's pretty much the same as we did before. And yeah, so there's a lot of work being done here. And I wonder, did we have the loop for the extra 100,000? Wasn't this here? It should be. Then it won't be any good comparison if I have missed this little part. That's a lot of more loops. I don't want to fool anyone. Yeah, this was inside of the apply filter. And let's compile this again just to check that we don't do anything stupid here. Now it's really slow. That's interesting. So it's actually slow to run on the GPU? That's not what I thought. Maybe we can see if it's as slow if we run it like this. Nope, much slower. So let's see if we remove this from this kernel again, just to be sure that we are looking at the same result. Yeah, we need to compile it again. (13), and then we run the Java filter without any extra things. 43. So there is actually a difference. It's not that large of a difference, but there is a difference. So it may not be that nice if we run run 1 million on the Java version or the actual data on in the kernel, because the kernel will be run over a lot of things simultaneously, but this will be run inside of the function. So there is a difference there. But at least we can see that they are quicker if we run them like this. And then I wanted to do one more test, because I thought that maybe I could get it to run fast on the CPU as well, just running a lot of them on the CPU. So I created this little runner here. that applies the filter over a set of the image, and this runner gets a start y and an end height. So this is actually an end y so I start at one point and then go to another point. So I will do some of the lines, but not all of them. And in my Java filter multi here, I have the same kind of code getting the image and so on. Then I will submit a runner that does 1/10 of the image, so a part of the image, to I split up the image in 10 parts, and then I run this fixed pool with 10 threads. And the reason I took 10 is that I believe my computer has 12 cores, and as I'm recording and so on, I wanted to use a lot of the CPUs, but not all of them. Maybe the recording will need even more than that. I haven't tried it. And then I create this completion service, so I actually will know when it is completed. And a completion service, if we submit some work to this completion service, we can actually take the result from the completion service, and when it's done, it will return. So if I take a value, it will be waiting there until it actually got a result, and it will take the first result it actually gets from the pool, and when I have gotten 10 result, it will shut down the pool and end it all, and write out the time, how much time it took to run this in a multi-layered settings. And it actually takes 55 milliseconds to run it, or 95, so it's as slow and even perhaps a little bit slower than running it linearly. I also tried it when I wasn't recording, and I saw the same result. So running on the CUDA graphics driver is much faster than running it on either linearly or over multiple cores. And because it's such a small example, I believe it's hard to make it faster just by doing it on multiple cores, because there is an overhead to actually start up the threads in the thread pool and then shutting them down and so on. So it's hard to, when you're not having a long running process, it's hard to actually make it go faster by just throwing more threads on it. But you can run quite small things on the GPU and do it really fast. Yeah, that was what I wanted to talk about today. This is how you set up something and run it on your GPU. You can always extend this and run in 3 dimensions if you want to, but much of the workload you do today you do in 2 dimensions. Even when you are going to machine learning, you usually do that with a filter over a 2-dimensional matrix. So I hope that you learned something today. I hope you found this interesting. If you have any comments, please leave them down below. Like the video and share it with your colleagues, your friends, and I really hope to see you in the next one.